Welcome everyone to QED-C's next Quantum Marketplace webinar covering Quantum Computing Systems 2. We did another one, Quantum Computing Systems 1 last month. You can see that on YouTube. Just quickly, some webinar logistics and format. Everyone is muted except the speakers. Please send your questions using the chat window once the presentations start. And also a recording of this webinar will be posted in the future on YouTube. Okay, in terms of an agenda, I'm going to give a couple updates on the Quantum Marketplace, quick overview on Quantum Computing Systems, and also going to have the lineup here. We have an exciting lineup today. Then we're going to get into a roundtable panel discussion and an upcoming webinar schedule. Okay, so Quantum Marketplace has a directory on the QED-C website. All the companies that have presented in the past have a little video icon there next to their name. Also, we do have a YouTube channel. You can go to just typing in YouTube/Quantum Marketplace, and you can see all our prior webinars there. If you haven't subscribed yet, please subscribe. We're gaining a lot of momentum here. This is our last webinar, which is Quantum Computing Systems. This is posted, already has 1,000 views on YouTube. Okay. Some overview of some trends. This is courtesy of BCG. We actually have Matt from BCG presenting today as well. And this is, I like this slide because it shows 100 plus potential use cases, covering areas of simulation, optimization, machine learning, and cryptography. And we'll get into this a bit more in the upcoming work here. The quantum stack is a little bit different than the classic computing stack. And this is just a reference from David Shaw. I think this is a great way to look at this, from the quantum plane all the way up through applications. And we'll be talking about more of that today. Also, just to clarify, quantum computing is not necessarily going to, replace classic computing. It's really a combination of what classic computing is best at and quantum computing is best at, so it leads to the best potential outcomes. Okay, and then also one unique thing about today is the three companies on the left that are presenting today are predominantly looking at a cloud access model. It's not to say they're not looking at on-premise in the future, but Anyon has a model who's presenting today of targeting on-premise only. So for selling to high-performance data centers, so you can actually do that classical and high performance together on site rather than in the cloud. And then also we have Q-CTRL today, which sells performance boosting capabilities to make these quantum computers run much faster. So we'll be hearing more about that today as well. Okay, getting into the lineup here, we've got Eric from Rigetti, we have John from SEEQC, we have Alexandra from Anyon Systems, we have Justin from Atom Computing, we have Mike from Q-CTRL, and we have Matt from BCG. So what's nice here is we have 5 companies that are providing technology in the space. We have one of the BCG representing the user perspective. So with that, Eric, you're up.
Great to be on with everybody here at the QED-C Marketplace. So I talked to Mark last week, and it's a wonderful program. Great to see the showcasing of different products and services in the space. So hopefully this is interesting for everyone. I'm Eric Osby, a VP Head of Product at Rigetti. I'm excited to share with you an overview of product and services today. So our mission, like many of the companies that are participating in this and members of QED-C, is to build the world's most powerful quantum computer system. We view it as a hybrid modality. So we think a lot about the classical compute as well as the quantum compute. And of course, the goal is to solve today's problems in a better way and solve problems we cannot solve today with existing classical compute. Rigetti has a growing product suite. So our core is the Quantum Cloud Services, QCS, offered access to our QPUs through the cloud, easy on, easy off. We also support a number of public and commercial programs, partners to our public sector partners in the industry as well. Also, Quantum Foundry Services is something that probably some of you don't know about. It's not well advertised yet, but we offer the ability to make coherent chips and some devices to spec for customers. And today it's a lot of university labs and government labs as well. So I'll walk through each of these today and tell you a little bit more about them. So Rigetti's approach, what's distinctive about what we're doing versus some of the other peers, and how do we fit into the ecosystem in quantum computing? So we have superconducting hardware, as Mark said, and this has been our core focus since we started in 2013. So we love the scalability of superconducting qubits, the high repetition rates, and the low error rates. But it's too early to tell what's going to be the final winning solution. But this is one of the leading players, and it's wonderful to see other modalities and other architectures as well, since we're working on this together. So as I mentioned, we really see high performance compute as critical here. And that's been a focus from day one for Rigetti with our integrated QPUs and CPUs back in 2017. We put our flagship devices online for our customers. We don't hold them back. And so the best devices that our teams are using, our algorithm developers, are the ones that customers and partners can use as well. A strong partner base, you'll see about a little bit more about this later, but an in-house quantum foundry based on our captive fab that we have in Fremont is a strong capability for us and for our customers and partners, allowing us to have a really fast product and engineering flywheel to make better QPUs as well as software systems. I'll go on. So we've been in this field for nearly 10 years. So our roadmap into fault tolerance, I think, is not dissimilar than many of the others, but I think the focus on the multi-cap processor is a differentiator for us. So coming from 8 qubits back in 2018 all the way to today, 80Q chips, which is our M1 processor online and available direct or via partners. And then we're targeting larger systems in the next few years up to fault-tolerant QC. And so we've already shown that we can actually have multi-chip processors with coherent capabilities on chip, and that's our M1 processor that's working online today. And so we're focused on this roadmap. We have clear areas of focus in error correction as well as algorithm development. We have a strong focus in QML currently in our team and with our partners, so that's a capability as well. Our cloud service, the Quantum Cloud Service, is from Rigetti. We offer not just integration of QPUs, our quantum processing unit, but also a cloud, low latency cloud resources through our partners like AWS is really critical for customers and users to not have higher latencies when they're running experiments such as VQ8. And we have partnerships with high performance compute facilities as well, like Oak Ridge and Fermilab, that we think is going to be really critical in the future. And so this is available today. It's been aligned since 2017. And again, as I mentioned, we offer access to our latest QPUs like M1, that's 80 qubits. Many of our users access through Jupyter Lab IDE that gives a really low latency connection, offers tutorials as well. We're offering high repetition rates through our systems, and the CLOPS metric is highly performant as well with a large grid. Currently, we allow users to access through reservations or on demand. I've seen that we really need to let researchers choose their own modality. So on demand is great. Through a queue, if you're testing circuits, you're picking the tires, you're debugging, but then when you're taking your larger data sets, especially for publications, the reservation mode, you have dedicated access for hours is really valuable for researchers. So here's a picture of the M1 that's online and available today through Rigetti. You can see the calibration reports and schedule reservation easily through our dashboard. So currently we have Aspen 11 deployed and Aspen M1. These are housed in Berkeley, California in our quantum data center. And we just announced last week, you may have seen it, that we launched our first out of the US QPU in Oxford available for our partners. And we'll build on that in the future. So I think that's going to be valuable for researchers in Europe, especially, to have those lower latencies available. I mentioned some of the commercial and government programs we have. You can see a number of our partners on here, like DARPA, NASA, Air Force. This is really critical. We have a number of milestone programs that are aligned to our roadmap, but also delivering on demonstrations that are valuable for the field as well. So we're part of the DOE Quantum Materials and Systems Center, one of the 5 funded centers, and it's a core area of expertise for us working with our partners there. Mentioned our quantum fab we have in-house, built in Fremont, and this is really helping us accelerate our efforts. We're moving recently to a new architecture that's a N by N grid, so just a 2D lattice that's very easy to understand and map quantum programs to. And we'll keep iterating on this as we increase the fidelities and the performance of those devices. We're also using this quantum fab to provide quantum foundry services where customers and users can send us designs for integrated circuits, quantum integrated circuits, caps, amplifiers, as well as we offer standard quantum test devices. So if you're building a new setup in your lab and you want to test the performance and benchmark it and calibrate it against a known device, we're able to measure devices fully in our fridges send them to you for your measurement as well, so you can calibrate, identify any issues or areas for improvement for your system. So this has been really valuable for some of our partners to have these standard quantum test devices. And that's it. I hope I got in the time, but I want to remind everyone of our quantum cloud services, the Foundry services, as well as the public and commercial programs that we're invested in. So thanks for your attention, and you can reach out to us at info@rigetti.com.
Thanks, Eric. John. Eric, we'll put you back on mute. You got kids in the background.
Okay. There we go. So I'm John Levy, the CEO of SEEQC. SEEQC stands for Scalable Energy Efficient Quantum Computing. And first off, I want to thank Mark, thank Crystal and Celia and the QED-C team for inviting me here today, and great that Matt's joining us as well as the other participants today. If we were having this discussion, a presentation around quantum computing, I don't know, 7, maybe 5 years ago even, we might ask the question around, can we build a quantum computer? Can it run an algorithm? Can it do anything you can't do on a classical computer? I think all of those questions have basically been answered, maybe the last one, some controversy. But where we haven't really figured out is, as an industry, is really to think about scaling, and scaling in a significant way. And so that is our sole purpose, is to function around a scaling model. And I'll see if I can make the case for what we're doing. So we're a company that spun out of a company called Hypris. Many of you may know us. We're the world leader in digital superconductive electronics, with its roots in IBM going back decades. Our systems are based entirely on single flux quantum. So we find CMOS circuitry great for computers and cell phones, etc. But frankly, too slow, require too much energy and heat dissipation, and too much noise. And so our systems operate typically between 30 and 40 gigahertz. We've built classical logic operating at 750 gigahertz, the fastest digital logic in the world. We operate at 3 to 5 orders of magnitude lower power, and we operate at a nearly zero noise floor. We do that in a chip foundry, not unlike Rigetti, although our chip foundry is for more classical electronics, but again, these are all single flux quantum as opposed to CMOS, so we see those advantages. And we have customers. We built some of IBM's first qubits back in 2003. We were building circuits for D-Wave. We built circuits for the DOE, DoD, NASA, etc. So we have lots of customers, commercial, government, and academic. So what's the theory of what we're doing? Well, if we go back to the early days of classical computing, we're seeing examples like this. This is a digital computer, the ENIAC computer, but it was never built to scale. It was, just so you know, it was highly error prone, lots of complexity, lots of cost, and it was built around vacuum tubes, which were obviously not going to scale. And it took, the invention of the transistor a year later at Bell Labs, the integrated circuit at Fairchild, the microprocessor at Intel, before you could actually get to something that was kind of enterprise grade. And this is the kind of thing that we're seeing at the IBM 360 as an example. So if we think about where we are in the quantum industry, we sort of think metaphorically we're back in 1946. And the image on the right is a typical superconductive electronic quantum computers, the likes of which you might see at Google or IBM or Rigetti or others. And what we think is that we need to go through this process of integration to build the world's first all chip-based quantum computer. And to do that, what we've effectively done is replaced all the racks of equipment, all the connectivity, operating at going from low temperature superconductive temperature to room temperature back to superconductive temperature, going from analog to digital to analog, all that complexity, cost, etc. And we've reduced it to a series of chips that look just like this. So this is a single flux quantum chip. This is in a reconfigurable architecture. This is an example of an entire control chip for a quantum computer. So imagine for a moment, if we go back to what this looks like and all the electronics that are needed to do that, and imagine you can put this in a multi-chip module where we have 5 picosecond latency between readout control and the quantum layer, and that you can do this in a way where we can operate at 20 millikelvin with control readout and control electronics. And then this is what an entirely chip-based architecture looks like. This is based on a computer that we're building on an application-specific basis for Merck. We've recently announced a partnership with BASF, and we have other commercial partnerships as well. But this is, to be clear, an entirely chip-based system going from the quantum layer all the way up to readout, control, quantum error correction, SFQ controller, classical memory, so we don't have to go out to the web for classical resources, and even a nod to cryo-CMOS for memory. And this is a computer that we're building now and is going to be going online probably within the next 2 to 3 years. Again, manufactured in our chip foundry in Elmsford, New York. We have facilities as well in London and in Italy. And our business model is very similar to what NVIDIA is doing on their cloud business, where essentially they began by building application-specific chipsets, which then migrated into their cloud system. So we're happy to talk to you more about what we're doing. We're actively working on corporate partnerships. We're, of course, always looking at investment, so we're happy to do that, and also working with quantum software developers. We're working with groups like QCware, Riverlane, and others, and happy to expand that for our platform. And with that, I thank you very much.
Hi, everyone. I'm Alexandra Daoud. I'm here to tell you about Anyon Systems, a Canadian quantum computing company. We are a provider of on-premises quantum computers. These are turnkey quantum computers, including the full vertical stack. Our vision at Anyon of quantum computers is that their greatest value will come as hardware accelerators for classical computers. For that reason, we want to ensure that they can be embedded directly into the fabric of high-performance computing centers. Anyon Systems was founded in 2015 in Montreal, Quebec, which is where most of our operations are based. We also have an office in Waterloo, Ontario, where we have a nanofabrication team. We are fully vertically integrated in that we design and manufacture most of the major components of the quantum computer. Our team of about 25 scientists and engineers design the qubits and the quantum processors, and we fab the chips in Waterloo. We design, manufacture, and assemble the cryogenics system, including the cryostat and the gas handling system. For the control electronics, we do the design, the layout, the verification, and the validation of our boards. We do all of the software and provide a software development kit, allowing users to interface with the machine to create quantum circuits and run them on the quantum computer. This is a little history of our journey. So when we started back in 2015, we recognized the need for quantum simulation tools in order to engineer large-scale systems. We set out to develop those tools, and those efforts were validated when Google became a client and used our tools in their development efforts. Over the next 3 years, we turned to hardware development. We fabricated our first qubit and our first dilution refrigerator. In 2020, we booked our first order from the Canadian government for a quantum computer, which was completed and delivered at end of 2021. And we recently announced a second order to a high-performance computing center in Canada, and we expect to deliver that machine in the first half of 2023. This is an image of what we call the Cube, which is the machine that will be delivered to the high-performance computing center. It's a standalone unit with 12 qubits. The cooling system inside is designed to allow for an upgrade to about 80 qubits with minimal changes to the quantum computer. Inside is our dilution refrigerator that can reach millikelvin temperatures, as well as our control electronics designed specifically for qubit control and measurement. Everything is packaged together in a single unit with a modular design to facilitate shipping, assembly, testing, and servicing. Our quantum processors host superconducting qubits and the circuitry for performing quantum gates and measuring the state of the qubits. Even though quantum computing is still in its infancy, we expect it to be very disruptive in many industries. Our quantum computers are the ideal platform for researchers looking to develop and test quantum algorithms, as well as visionary organizations looking to develop a quantum expertise. We're open to investors to help with our R&D efforts and to providers of tools that can complement our offering. And of course, we're always looking for talent to join our amazing team. Thank you very much for your time.
Great, thanks, Alexandra.
My name's Justin Gang. I'm Chief Product Officer at Atom Computing. Looking forward to introducing our company today. So our mission is to deliver scalable quantum computers. We are hardware focused, building gate-based quantum computing hardware. And we will be launching a quantum compute as a service model next year as we go commercial. We have prototype system now that we're working with partners and some early customers on, and we'll move towards the full commercial system in the coming year. So our technology, like other neutral atom companies, uses optical tweezers, so finely focused lasers that actually hold individual atoms in place so that other lasers can operate on them and control their quantum information. Different from other neutral atom companies, we use the nuclear spin of the atom as our qubit rather than the electron spin. So we use alkaline earth metals as our material, and they have a unique property of having a complete electron shell or a closed shell, which provides protection to the nuclear spin from environmental perturbation like stray magnetic fields or things like that. And this results in long coherence times. Long coherence times can be quite useful. So we recently published a paper about our record-breaking 40-second coherence time, and this is not a limit. We can continue to work on this and increase it. Coherence time becomes really important when it's paired with some things like mid-circuit measurement, where you can take some measurements, go and compute what you want to do next, and then come back and continue your operation. So super critical for quantum error correction, as well as certain hybrid algorithms. So our view of the quantum industry is that there was a time when people doubted whether quantum computing hardware could exist. And thanks to some other players, that has been proven. Yes, they can exist. And then it was, well, can they have the fidelity that we need to get to? And other players have come along and said, yeah, here's really high fidelity. But the question that we see now is, can systems scale? And that is where our technology will shine. So we have the ability to scale up quickly, apply this towards physical qubits, towards logical qubits, and then start to explore these applications that everyone talks about. So how do we scale? So we create more traps for our laser. So we have more lasers that we put into a 2D grid now. And so our prototype system that's 100 qubits is a 10 by 10 array. Over time, we'll move to larger two-dimensional array, and then move to 3D after that. And if you imagine 100 by 100 by 100 array, that's 1 million qubits. And our atoms are spaced at 4 microns apart. So what that results in is 1 million qubits in less than 1/10 of a cubic millimeter of space. And this is all within one system. Now there's a room size supporting system with all the lasers and control electronics and things like that go into supporting where the qubits are operated on. But as we scale from 100 to 1 million qubits, we'll still be within that same size, and the room size system will be about the same size room size system. So this is why the scalability of our technology is really exciting. So here's a photo of our 100 qubit system. It is a little bit like a science experiment looking device. As we move to a commercial system, a lot of these things get buttoned up, modularized, really controlled optics. We know exactly what we want to have, and we can make this in a very clean way. So you'll see a change in the view over time. And if we wanted to peek inside and see where the action takes place, deep inside that computer is an area where we have a glass cell where we're holding our atoms and doing the operations on them in that blue area. So neutral atoms has not been talked about too much in the quantum scene until recently. And so people think, oh, this is a new technology. But actually, it is based on a lot of work that it was done much earlier. So optical tweezer work and laser cooling, which are essential to executing. These are technologies that were done as far back as the 70s and 80s and earned Nobel Prizes. And some of the theoretical work around neutral atoms was actually done in 1999 and 2000, where the hardware and the systems to control them weren't quite ready, but the idea was there. And so after a few decades of continued work and technology advancements, neutral atoms are ready for implementation now. So what's next for us? As I mentioned, we're developing our commercial system and we'll launch that cloud service. But in the meantime, we're working with partners and customers. And so interested folks who want to collaborate should reach out. Please do. And here's some information to contact me. Thanks.
Great, thanks, Justin.
It's great to be here. My name is Mike Biersick. I'm the CEO and founder of Q-CTRL. And our objective is to make quantum technology useful for the vendors and also useful for the many end users who would be listening to this call as well. Our focus today is a little bit different than the other companies you've heard from, but it's complementary. We build infrastructure software with the aim of delivering useful performance and accelerating the path to quantum advantage. If you like these analogies, we're like the turbocharger to the supercars that are built by all of the different companies that you've heard from today. We build tools for application enhancement that is hardware optimized application modules. We build tools for error robustness and noise aware compilation. We build tools for hardware stabilization and AI automation. And of course, like many other companies who are active in the field of developing practical quantum error correction, you can read about some of our work in that in IEEE Spectrum that was just published yesterday. And quite importantly, our tools are technology agnostic. We provide everything from the quantum firmware, which touches the control electronics, all the way up through compilation and quantum error correction in a way that works across the different modalities that you've heard from today. We're the world's only trusted provider of quantum control solutions and quantum control infrastructure software. We service national laboratories around the world. We have commercial partnerships and commercial relationships with a wide variety of companies, including 2 that are actually on this call. We sell to academia. We also are very active internally. Overall, we have about 5,000 individual users of our software. Our R&D team has run more than 12 billion jobs on IBM systems as we've developed core technology. We have announced major partnerships already with Rigetti, with IBM, with AWS. We've worked with Rigetti for a number of years. And for what it's worth, we've appeared in a variety of media outlets. The core of our offering to the end users of quantum computing is the realization that quantum computers are exceptionally unstable and exceptionally prone to error. If you do the math, it turns out that these systems, even the absolute best being provided by all the different companies around the world today, are about 24 orders of magnitude more likely to suffer an error in a computation than a conventional system. And this leads to obfuscation of the insights that customers actually want. So if you think about what you should achieve with Grover's search algorithm on the left, when you actually run it on a machine, even at very small scale, this is a 5-qubit algorithm, you get nonsense. You get something that is obfuscated by the noise. But if you run it through our software with actually, in this case, a single line of code, you can have this binary transition that converts the hardware into a system that gives you a useful output. Overall, our contribution is to turn these very well-engineered bare metal hardware servers, the bare metal QPUs, if you will, to use language from the cloud domain, into quantum processing units that give you real insights. Now, we have shown in head-to-head comparisons on real commercial superconducting quantum computers, in this case, up to 9,000x improvements in algorithms using our software, again, in a zero config setting. This allows our customers and our partners to gain insights that otherwise they simply could not get, as per this quote from Be It Tech. The core product offering for end users is a tool called FireOpal. This is previously announced to be forthcoming this year on AWS Bracket, and it is exceptionally simple for the end user. The end user who has developed their own application for either their production workflows or their R&D simply feeds a description of their circuit into our software. Everything else happens in an automated fashion, including the connectivity to the hardware backend. We return to you an answer that has improved utility to you. Now, for anybody here who's an expert This is all about automated error suppression at the gate level and at the hardware level. It is exceptionally efficient. It's also 200 times cheaper to run than any of the sampling-based approaches because it is deterministic. And the last thing I'm going to say is that if this is not quite you're not quite ready for this, we do offer the best EdTech tool in the world for quantum computing. It's called Black Opal, and you can get access to this from our website along with all of our other documentation. So thank you very much.
Great, thanks, Mike.
So thanks so much, for all to you, Mark, and to Celia, to Crystal, for having me here to represent a bit of the voice of the end user among these hardware providers. And the first thing I want to start with is just a little bit of what motivates end users to invest in quantum computing, invest their resources, time, et cetera. And really it comes down to this, we see investment across the board, but it's especially concentrated and acute in industries like finance, pharma, materials, that in some ways have failed to keep pace with market returns because of the absence or the want of a technology platform to drive growth, like tech and in other places. And so what's happened in these industries is that discovery, innovation, and value creation is somewhat thwarted by rising costs in the absence of major tech innovations. Pharma, for example, it's 3 times the cost to discover a drug as it was just 20 years ago. Banks, in finance, it's higher cost of equity than return on equity for most banks, and 60% of European banks. And then, EV batteries, obviously, which are a really promising technology, demand outpaces supply by a factor of 10 these days. So these are some of the reasons that, that people are looking for next-gen compute platforms. And quantum computing is really, the prime example, top of mind for many of our customers when it comes to this. And so I guess 2 sort of phenomena I think that are worth noting about customer interest in quantum computing, even in the last, say, 6 to 12 months. One is that it's getting pretty broad. So you see a set of industries here, but we get outreach from all sorts of folks. I mean, recently the head of a major national fitness chain asked me about optimization use cases for scheduling optimization. It may not work out, but I think that the point is that it's really interesting, and actually it's a great indicator that we're getting this kind of interest really from across the board for the kind of quantum interested. The other thing I would want to note is that in these kind of core industries where there are sort of well-established use cases, the interest is just getting deeper and deeper. Nowhere more so than in finance, where you'll see that finance companies are hiring directly to address a number of many of these use cases here. And this is, we've listed 15, 20 use cases here, but there are any number that are under active exploration by the likes of JP Morgan, Goldman Sachs, Barclays, et cetera. And I think the thing that I want to mention, more so than the use cases themselves, is just kind of what the process typically looks like in terms of activating quantum computing at these companies across industries. And it's really kind of a sell, skill, and scale kind of process. The first thing that typically happens is that you need to secure some level of executive support, whether it's funding, whether it's a regular cadence that helps keep research the capability forward. The second is skilling, and that's really building a capability. Sometimes, as I mentioned in the finance case, it's by directly onboarding folks. Sometimes it's upskilling folks that you have in-house already. And then oftentimes it's done through partnership. And that last piece, scale, is an important part of what we're doing as well, because you really need to scale the rate and pace and breadth of your experimentation with quantum computers, which of course requires increasing attention on vendor selection. And so I think that this, like number 2 and number 3, the skill and the scale phase, are really ideal sites of partnership with quantum tech providers, like the ones that we've just heard descriptions of today. And when I think the last thing I wanted to kind of focus on is when we think about partnerships. we're often asked as BCG, well, who do I focus on? Now at this point, and it's a great thing, there's a set of potential providers, and how do we choose which one? There's an answer kind of for investors that's slightly different. But when end users ask us that, there are kind of the tried and true kind of like holy trinity of things that we say to look for. The one is, of course, talent, right? And you want to really find a team, at the provider level that is talented. You want to find a team that has an ambitious and yet credible technical roadmap. That's all important. And then I think increasingly, and companies are getting better and better at this, and I mean providers are getting better and better at this. You want folks that can offer onboarding, upskilling, various kind of capabilities that really facilitate not just access to the compute, but actually that capability building. The last one that I think is becoming really important is benchmarking. As we approach a period in which quantum computers are actually kind of sidling up toward quantum advantage, where they'll be able to do real things, beyond the capabilities of simulators and beyond the capabilities of classical computers, companies are asking us from a vendor selection perspective, well, how do we benchmark these things? Systems benchmarks are fairly well entrenched, and of course, quantum volume may be the most cited one. But we are finding, and that works really well, of course, for investors, and it works well for very sophisticated users of the technology. But as the kind of pool of users expands, we think that there's going to be, and there's already, this is already a bit nascent, increasing focus on application benchmarks, which answers questions like, okay, well, I am a pharma company, so what quantum computing physical implementation works best for Hamiltonian simulation, say? Or I'm an investment bank, and so I have a kind of linear algebra focused problem. And so we think that application benchmarks are, just as they did in classical computing, coming more and more important as a way to determine who the ideal partner is for these end users.
Okay, so we're going to get into the roundtable discussion here. And I think for the quantum computing companies, start with John. Are you a full stack quantum computing provider? And can a third-party software for quantum providers work on your platform?
Yeah, so we're a full stack quantum provider with a caveat. So I should be really clear. We build application specific quantum computers, and it's going back to Matt's point about application benchmarking, because we think that where the state of the technology is today, the idea of being able to work with a quantum software developer and co-design a quantum computer that has the potential to scale and do it to solve a very specific set of problems is kind of where we are today. So the way we do it is we co-design with our software partners the equivalent of what's almost like a quantum ASIC, except it's an ASIC that can scale. Where we're going is to build reprogrammable quantum computers that are like quantum FPGAs, which we have a patent for, before we get to general purpose fault tolerant quantum computers. But again, the point here is that we partner with software vendors to co-design application specific quantum computers for our end users.
Great, thanks, John. Eric, you care to comment on this?
Yeah, in terms of Rigetti, what we provide?
Yeah, exactly.
Yeah, Rigetti is one of the full stack providers. So we have the service, which provides access for QPUs, but we have full stack with the compilers, optimizers, etc. So yeah, we are, and I think that really helps us develop solutions for end customers that they need. It needs to be integrated. We work with partners. We heard about Q-Control today as well, so that's critical. But I think having the ability to make modifications to the stack is really valuable. As we heard about application-specific QPUs. I think long-term, we will have application-specific quantum processing units. We're not there yet. We don't know those requirements, but I think that's going to be part of the future. So yeah, we're one of the full-stack providers. And I think it's great to have multiple of these, and it could be in the future that different companies provide different types of quantum processing units for different applications.
Yeah, great. Thanks, Eric. Justin.
Yeah, so I would say we're not full stack at this point. We are hardware focused, and we have an interface layer that's based on OpenChasm API, so open source language that allows people to connect through whatever software framework they want to work in, whether that's Qiskit or Cirq or other types of things that'll tie in through that API, come in and use it. And then sort of to the second question, if you are a third-party software vendor and you want to have access to our system, you should come talk to us. We have a partner program. We're definitely interested in working with folks who are developing algorithms and interesting things. And particularly, we're looking for those partners who can help us demonstrate some of our differentiators and do cool things with our unique capabilities.
Great. Thank you, Justin. Alexandra.
Yes, thanks, Mark. So we are definitely a full stack quantum computing provider. We have the entire hardware stack, and we have a software layer on top for users to interact with our machine. We have a Snowflake framework, which we just started to make open source, and anyone can see it by going to our website. And third-party software can definitely work on our platform.
Okay, great. Mike, do you want to add anything to this and where you guys play?
Sure. I mean, I think you've heard more or less the same answer from all of the hardware players, that almost everybody considers themselves full stack. I think maybe the operative question is whether they engage with third-party providers. We absolutely support the idea that having expertise from the hardware up is valuable in-house for all of the key players. But there are some things that specialist providers simply do much better. And I think Q-CTRL is an example of a company with a singular focus on improving the performance of hardware in all aspects of this infrastructure software. It's a little bit like, if you like these models, again, it's like VMware, right? We go from the bare metal up to the usable platform. And we're very happy that we get to engage with actually several of the companies on this call and on the last call as well, providing those kinds of solutions.
Great, thanks, Mike. Matt, anything you want to add on this? Any perspective you're hearing from customers?
Well, no, I mean, the only thing I would say is that, I think that there are some advantages, and like I think historically we would have said partnering with a full stack provider is sort of absolutely critical. But I think that more and more systems are becoming kind of integrated with software players. And I think that there are just more partnership options open. And to Michael's point, that includes things like accelerators as well. And so I just think that I think there are certain advantages for sure by being a full stack provider. But I would just say that the partnership options have become more nuanced and varied, and that's a good thing.
Yeah, great, thank you. Okay, so so we're going to change paces here a little bit. So maybe start with John again. How do potential customers best assess various quantum computing solutions today, and potentially your solution?
Yeah, I mean, I think that one of the things that people tend to do, companies tend to do, is there's a kind of focus, a singular focus on qubits and or kind of quantum performance by some individual metrics. And companies tend to emphasize the things that they're best with, right? So some will have long coherence time, some will have really good fidelity, some will have great gate speed, etc. And what we find is that you need to think about these quantum computers as entire systems. And where you're thinking about coherence and fidelity and gate speed, latency, cost, noise, system complexity, uptime, error correction, connectivity, everything. And that you need to then think about them in totality, because quantum computers at the end of the day are computers. It would be a little bit like analyzing classical computers by the performance of transistors. It's just not where you need to think about it. So you need to think about them as coherent systems, and then how those systems are there to solve your specific problem, not somebody else's problem, but what you care about and what you think is high value.
Yeah, great, thanks, John. Eric.
Yeah, so in our experience, it really depends, and customers oftentimes are looking for insights and feedback on what do you offer, what are the differentiators, what can we do with your machine. So it is early days. I like the point about transistors versus the overall computer performance. I think it varies. We have really valuable quantum algorithm developers and solution experts and consultants in QCware and Zapata, for example, among others. They play a critical role in needing to know and understand the performance and differentiators of the quantum hardware providers and the full stack providers. And their customers are looking for that advice as well. So it really depends. The ones that we're focused on are the ones that really want to contribute to the field and want to add capabilities, that want to show the performance of the devices, that want to use a full toolkit, that want to contribute to the code base as well. But they're looking to understand the state of the art today, what can be done, what are the advantages of them, and then can they partner with your team? So what we hear a lot at Rigetti is not only can we get access to your QPUs, how's the performance, what's your roadmap, but then where are your experts aligned? And because they want to collaborate on projects. And so it's still today, I don't think it's enough to offer just turnkey, no-touch service. We're not quite there yet. I think there needs to be interaction and feedback and collaboration, and that's critical.
Yeah, right. Alexandra.
Yeah, I'd say that the answer to this question is different today than it will be when more full solutions are available. Once there are more fault-tolerant computers out there, then it'll be sort of a different analysis that potential customers will have to make. As of today, given the solutions that are available, it really is based on need. So, our on-premise offering gives flexibility in terms of use, timing, scheduling, and IP rights on whatever you're running on your machine. So if your specific needs revolve around those, then you would most likely turn to an on-premise solution versus a cloud solution. So it really depends on what you're looking to do right now with the machines that are available right now.
Okay, great. Justin, wrap this up.
Yeah, great answers from the panelists so far, and I'd agree with a lot that is said. I make a distinction between customers who are using quantum computing as a research tool versus those who are maybe an enterprise type customer who's thinking about the applications. And I think based on which kind of customer, they're going to choose based on different things. Researchers are often looking to say, how can I make my algorithms better? Or how can I get more creative with my algorithms based on the capability of the system that I'm using? And I think from that point of view, they're excited to get on every possible system so that they can take advantage of unique capabilities. And from an enterprise point of view, I think having sampling a system, but I think as Eric was pointing out, they're thinking about the business implications too, wanting long-term partners, good collaboration partners, know that they're working with people who are in it and over the long term. So I'd agree with that. Yeah, great. So I want to go to the second part of this question and start with Michael. So Matt brought this up earlier, but how important is hardware system and application benchmarks in this assessment? Michael, since your software is really adding massive performance gains to some of these systems, how are you looking at this?
It's a great question. I think from the end user perspective, the starting point is to ask yourself two questions. First, do you get useful outputs from a particular hardware system for the problems you care about? We heard an allusion to this earlier about these proxy metrics. It's actually a great tie-in because if you think about something like high performance computing, classical computing, no quantum at all, even though it is commonplace to quote a metric like flops, right? We talk about petaflop or exaflop machines. For the experts who know, those metrics are quite useless when it comes to the applications. What we care about is a wide range, a suite. It's the LINPACK benchmarks or analogous system suites. So we think about proxy benchmarks in quantum computing in a similar way. They give some insight, but we really want to ask about the benchmarks that are most closely related to the problems that the user cares about. I would say the other part of it is a question for the end users. Are you able to get those insights without being an expert in the hardware level operation of the system? Now, clearly this comes to a point of bifurcation. Some people are research experts and want to really think about what we would call the Hamiltonian level, what is really going on at the hardware level, because their goal is understanding. But for enterprise end users who are trying to solve a problem that they care about for some kind of strategic advantage, starting to make this kind of gap between what is going on with the proxy metrics that are really talking about characterizing hardware and the end user value is the core area where I think where we think they should focus, and that is again where our software is delivering the most value. Oh, Mark, you're the muted one now.
Mark,
Thank
you're
you.
still.
All right, yeah, thank you. You're right, Mike. Thanks for that, Mike. That was insightful. John, you want to comment on this quickly?
Yeah, I mean, just briefly, one of the things that we do when we engage with customers, one of the very first things we do is to try to understand the best classical performance for the problem that they're trying to solve, so that we can benchmark that and we understand exactly, because they're whoever they are, they're going to be, the experts or nearly the experts in that particular area, so that we can actually assess whether or not we can offer a performance gain for them on a quantum basis and what that might look like. And so involving classical benchmarks and then compared to quantum performance is really the metric that we're trying to go after and make sure that there's value created.
Okay, great. Justin, you want to add on this?
Nothing in particular other than that, I think benchmarks are always going to be useful and we're always going to need them. And I think everyone should be open-minded about what those benchmarks are, because they are constantly changing, and no need to lock in immediately is my opinion.
Okay, great. Eric, Alexandra, anything extra here?
No, I think I agree with what was shared. I think the application benchmarks are really critical. And I think it's important for there to be alignment. And there's been some efforts, Quantum Benchmark, for example, that was acquired by Keysight, played a role and continues to play a role at Keysight. So I think that third-party verification is valuable for users, for customers, because it really depends how you use the machine. So Rigetti is going to be able to operate the machine at a higher level than someone that just comes in cold. We want to close that gap. That will close over time, but it's still the case for, I think, all the providers are publishing papers with their in-house, specially trained people. So closing that gap is critical, and sharing and letting third-party come in. QED-C has done some nice efforts here in benchmarking. So support those. It'll evolve over time, but the more we can share, the better.
Great. Alexandra, anything to add?
I agree with most of what's been said up to now. And I would add that a typical algorithm developer would naturally care about gate fidelity, especially 2-qubit gates, and about crosstalk. And unfortunately, not many vendors have published systematic results on crosstalk. So there's still a lot of work to be done to have sort of this uniform approach where we can compare apples to apples and oranges to oranges.
Yeah, great point. Okay, so I'm going to dig into this a little bit deeper, and this is actually courtesy of Matt from BCG. So Matt, why don't you take us through this from the high level and how you're looking at this?
Sure, and I mean, without kind of draining the chart, I would just say that on the left you have traditional systems benchmarks, and then on the right, as you move to the right, it's a bit of a spectrum toward application benchmarks. It's very, very similar with classical hardware, right? Where obviously there's a set of folks that are really interested in teraflops and things like that, and then there's another set of folks for different use cases that are interested in ML-perf sorts of benchmarks. I think the point here is that what we're recommending is to take a bit of an integrated approach when you're evaluating hardware vendors. First of all, always think about talent roadmap and partnership capabilities as sort of a first pass. To the extent that you delve into the systems themselves, which is increasingly important, as I say, as real applications draw nearer, what we think is really, really important is actually doing a little bit of work to move to the right here. And some important things are I think that Michael, you may have mentioned the quantum benchmark, SuperTech, which was recently acquired by Quanta, has a similar approach, and QED-C itself has a similar app-oriented approach. And I think that there's a couple important things. One is that there are a set of near-term algorithms that are in common use, and so those invite comparison. Things like VQE for chemistry, battery development, these kind of chemistry simulations, QAOA for finance, for logistics, things like that. And different hardwares have very different performance capabilities on the different algorithms. And there are a set of features, performance features, things like critical depth, entanglement ratio, measurement, parallelism, liveness, things like that. And so I think that what's interesting is that you can benchmark, if you know what algorithm you want to run, you can kind of benchmark along those dimensions. And then the other is it operates a little bit like a feature vector, where if you know that an algorithm is sort of related to one that's benchmarked in one of these suites, you can use that as a little bit of a proxy for, for the problem that you're trying to solve. And, it's not perfect, but I think increasingly we'll see companies more and more leveraging these application benchmarks to make some decisions around who they decide to partner with.
Yeah, great. Anybody want to comment on Matt's comments? John?
Yeah, I was just thinking that, there's so many different parameters here. One of the things that I think about is, gate architecture, and, are you using CZ gates or CNOTs or Givens gates, or, like what kind of gates are you using, and how does that flow through? But there's just so many parameters here. And Matt, as you were talking about, then running different algorithms, you can say, oh, I'm parameterized in a certain way, and this is my benchmark, and then you run an algorithm and suddenly, everything, changes. And so it seems to me this is really an open question, and I just feel like we're so early days in terms of our development as an industry that I'm really glad people are thinking about and doing this, but it just feels so bespoke as a function of the very setup that you're doing for the very problem you're solving with the algorithm you're using. And it's going to be really hard to do apples to apples comparisons.
Right. So I'm gonna jump forward since we've covered this a bit, and I think a lot of questions come from what's a customer to do, right? So how does a customer best use these benchmarks, even though it's early? As you said, John, I think everybody's going to agree with you there. Is how do they use these benchmarks to evaluate how this applies to them? And I think some of you actually brought this up earlier in some of the other questions. Is everybody's got their own use case, right? So how do they evaluate how to move forward? So John, I'm going to go back to you on that.
Yeah, okay. I mean, again, I think it goes back to how much can you tailor a system to optimize every parameter to solve the only problem you care about. And say, like, for example, when we work on co-design with our software partners, we're trying to reduce circuit depth, right? I mean, as an example, because that has an exponential, increase in terms of performance. And so you just have to think about what's my algorithm, what's my architecture, what are the hardware resources that are needed to run it. How can I, we get 5 picosecond latency between readout, control, and qubits, right? And so you're trying to figure out all of these things, but it all goes down to the thing you're trying to do, and not sort of some demo that somebody wants to run for you, or even something that sounds like what you want to do. You really need to go and drill down and understand deeply what it is you want to accomplish on that platform, and then see what people can come back to you with.
Are you with SEEQ, are you partnering with customers deep enough so that they can learn
Yes.
about that without being overly exposed before they figure out if it's going to work for them or something?
Yeah, and so we do that. That's a lot of the work. It's funny, earlier today, we were doing just that with a big financial services company, and we were doing exactly that. We did with Merck, what we're doing with BASF and other companies.
Great. Thank you, John. Alexandra, you want to take a shot at this?
Yeah, I'm going to throw back to something that Matthew said earlier, which is finding the right team with the talent. I think that it's a lot about fit, and it's not just about technology fit, but it's team fit. So as a potential customer, it's up to you to talk to as many people as you can, to speak to the individuals that are involved in the actual development at these companies and see what works best with you. Who do you have that fit with? Do you feel the credibility of the team that you're working with? And that's something that we certainly encourage. We invite customers to come and test our software, our hardware. We've had a team come in and run algorithms on our quantum computer, and they were blown away by what they saw. So it's really about doing the homework, speaking to people, and finding a team that you're comfortable with.
Yeah, great. Thank you. Justin.
Yeah, I think that there's a lot of criteria when a customer is thinking about it. I agree with what has been said so far. And I think another piece of it is customers need to think about their long game. So how quickly are they going to get to where they need to be with their hardware? So it's not just what computers are doing today, but what is their plan for growing, scaling capability, hitting whatever benchmark you choose at some later date. How is it going to get them to actually implementing in a utility scale their application using quantum computers? And I think it's a little bit of a bigger picture in terms of what they need to consider. Their scorecard of who to engage with is bigger than just whose system is best today.
Yeah, great. Thank you. Eric.
Yeah, great points by the panelists. I would just add that as customers are looking at evaluating and trying to use benchmarks to decide who to work with or when to work with them, I think the really good customers tend to have worked with a lot of the players, right? Because they want to educate themselves. They want to see the individual advantages of each of them. And so they're going to look at the benchmarks, but I'd say they're not yet there in a very digestible manner. So they're going to look for the publications by the different providers. They're going to look for the experts on the team. They're going to look to see what's been run so far and how well it matches. But in my experience, what's been valuable is to try it. That customers just want to have an easy way to get on and try and see for themselves. And that's valuable internally for them as they're building support for quantum computing, is to actually say they've actually been a part of the quantum computing project. And they to use an earlier example, they've driven the supercar themselves, right? So I think we haven't talked too much about doing a prototype example is really valuable for customers. And so my experience is the ones that seem most agile are trying a lot of the different providers and their systems to educate themselves. But there's so much rapid evolution that this longer term partnership is really valuable because these systems are evolving. You look at all the announcements from INQ and IBM.
I was curious, I like that. So you're saying that customers that are evaluating this should be working with more than one potential vendor set to learn what's best going to work for them and team and everything else. Mike, you care to comment on this?
Yeah, I think Eric has raised a really important point. And I want to, throw one factoid out here that will totally muddy the water on these benchmarks. We talk about QAOA, for instance, as if it is a thing. QAOA is a whole framework for running.
So what is Mike? What is QAOA? Not everybody knows the acronym.
QAOA is an approximate algorithm that is used for certain optimization applications. So there are some problems in, say, transport optimization that we've worked on and other even chemical applications that can use this hybrid approach, a little bit of quantum, a lot of classical, and a feedback loop in order to get some insights. But QAOA is not one thing. in fact, a lot of these benchmarks are not one thing. In fact, for QAOA as a specific example, our team at Q-Control, because we work on this hardware optimization part, we built a module for what's for the experts. It's called the hard mixer in QAOA that uses exponentially fewer qubits than the best published standard. Now that means that you can get much more performance from the same hardware with this version of QAOA than some other version of QAOA. Now, this leads to giant complexity for the end users. And I think one of the biggest areas of growth and opportunity is in testing the waters across different platforms, as Eric suggested, via services like Alify Ripple, which connects to multiple backends, and in particular, some of the platforms like Bracket from AWS, who allow a user with limited overhead to connect their application and actually run head-to-head for themselves on different systems.
Thanks, Mike. Matt, anything you want to add?
No, I think that those points are really well taken. I think Michael's builds on a little bit of what John was saying earlier, that like we are in like very early innings when it comes to application benchmarks. And so I think maybe just another thing I would say is that to the extent that you are looking at application benchmarks, hopefully in complement with your systems benchmarks, it does help to have a technical advisor, right, who can kind of guide you through some of the complexities that both Michael and John rightly bring up.
Yeah, right, great, thank you. Okay, I think I'm going to start with you, Matt, and then have some of the others comment on this. So, we see pharma, we see materials, we see various, segments of the market having potentially early quantum advantage. But, and this might be a little contentious, but, in terms of, the clients that you and BCG, consult to, where are you seeing the biggest pull? Where are you seeing customers spending real money, hiring real talent, making the biggest commitments, and seeing potential upside, and maybe not even the closest in terms of timing, but who's most aggressive?
This is a really good question, and I think we get asked this question a lot. And I would say, with folks within the industry, I think that they're often sort of surprised that like where quantum computing is the very most applicable, maybe in a near term, is not necessarily where we're seeing the highest industry pull, because of course it's a two-sided equation, right? There's like there's a lot of different factors, right? But that's sort of the supply side, but then there's the demand side, and and there are a lot of different factors there. I would say that the place that we're probably seeing the most pull might actually be finance. It's not to say that, and some people are surprised that it's not either chemistry for drug discovery or for materials, but there's a number of different things and factors that go into it. For one thing, in finance, there's a kind of rich history of actually having some success with physics-based modeling to accelerate, market simulations and things like that, right? That's one thing. For another, there's a lot of competition in this space, and a history of a willingness to invest in, vanguard technologies. And then for a third, I think that in certain industries like drug discovery, for example, you had a lot of promises that were made by technologies, computational technologies in the 90s that were supposed to really accelerate things. And those didn't really pan out. I think the tide's turning a little bit as AI approaches in drug discovery start to actually create a lot of value in the last 2-3 years. So we'll see whether there's a knock-on effect for quantum. But I think that, in finance, you've seen just a really deep concentration of interest, including direct hiring, including partnerships. That's one place. I think materials and pharma are close behind. And then you have industries like, energy, oil and gas, which is like the use cases may not be as obvious and clear cut and maybe not as near term, but the need for innovation is extraordinarily pressing and urgent and acute. And so we're actually seeing a lot of interest, both from traditional kind of oil and gas, as well as from, folks that are experimenting with green and new forms of energy efficient alternatives.
Yeah, great, thank you. Justin, you care to comment on this?
Yeah, so I guess I would go back to the idea that it's implicit in your question that you're talking about industry segments, customer industry segments, but actually customers of quantum computing.
I wasn't differentiating between defense and industry. It was apologies if it came off that way.
Well, just that there's, largely there's the enterprise, but also government, but also academia. So large number of users of quantum computers that come from just purely doing research on the system. So sometimes people will say, oh, quantum computers don't have value today. Not true at all. They provide a ton of value to those researchers who are developing these applications. But in that industry segment, I think a lot of what Matt said was, I've seen the same type of thing. It's actually more around the types of problems, as there's these optimization problems or simulation problems or acceleration of machine learning. Those categories are what are driving customers. And so it's a variety of segments that come with those types of problems. In fact, it's hard to pick an industry where companies are not affected by at least one of those types of problems. And so, if somebody's sitting in some industry thinking they're safe because nobody has looked at it, they're not. There are people across almost every industry looking at quantum computers, and they should take that as impetus to go and get involved themselves.
Yeah, Alexandra, you want to comment on this?
Yeah, I agree with Justin. There's the in industry, I would say that a lot of the big players in each of the different industries have jumped on board already and are looking into this. And then there's academia and there's government, and around the world you can see governments investing in quantum. Like it feels like the announcements are monthly, that a new government somewhere around the world is investing a very large sum of money into their quantum strategy, and that they're hoping to move things forward. So we definitely see the interest everywhere is peaking.
Okay, Eric?
I agree with what's been said.
Okay, great. John?
Yeah, I think that we're going to see more actual coming out of governments around the world. Increasingly we're seeing, individual governments deciding they need to have, the first quantum computer of and fill in the blank country. But I think that there's going to be a lot more. And if you look at the U.S. Innovation and Competition Act and the CHIPS Act and all of those things, I think that you're going to start to see the U.S. government being a much more aggressive customer, a sort of supporter and customer of quantum computing devices, from chips all the way up to systems.
Yep. Mike, you want to comment on this?
Yeah, I think government as customer is an exceptionally powerful driver of this sector. I saw that when I worked at DARPA, how DARPA could shape whole industries. I think we're starting to see the same thing today. One application area that we've had quite a lot of interest in is optimization for logistics. It's in a sense not as sexy, but it's an enormously impactful application. Just a back of the envelope analysis shows that because of the standard tools that are in use today for transport optimization, they're very, very good classical heuristics for understanding how to timetable buses and ferries and things like that. They leave about 2% on the table. And that 2% in a place like New South Wales, which is where Q-CTRL has an office, that's like 21 million hours of time wasted for commuters per year, just based on that little bit left on the table. Because of that, because you don't have to do perfectly, you just need to eat a little bit into that lost efficiency.
Because it's so big, right?
Yeah, that's right. We see that optimization for transport, for logistics and the like, for defense and civilian purposes is a very high opportunity area.
Great, thank you. Okay, with that, we're gonna just go. Well, I don't think we have time for this one, unfortunately. But I do want to make a comment. In terms of the upcoming webinar schedule, we have many people have suggested that we basically get into the topic of talent. It was also brought up again today. So we have bolstering talent for quantum coming. We're targeting July 28th. Actually, there was a question in the chat. And this sort of leads up to this particular person's actually going to be presenting in this webinar, is if you're unable to upskill internal talent, how are you currently finding new people to join, and what are your biggest limitations you face when doing so? So look forward to seeing you all then. Thank you.